One of the issues that I see beginners have with FEA analysis is they get confused with the difference between force and pressure. So to illustrate that, I'm going to do a little magic trick here. I have put my shoe onto the sheet of paper and I've traced out the profile of my shoe. What I propose to do is I'm going to stand on somebody's chest and give them a $20 bill for the magic trick. Now before we get any volunteers, let's look at this, take some consideration of what we're proposing here. So I've gone ahead and extruded my footprint, and let's see what the area is of this sole of my foot. And so I'll go to the inspection tab and let's set precision, let's say on 1 decimal place, and I'm going to do it in both inch and metric units. And so if I select this, I see that the area of my foot is about 41 inches or about 26,000 square millimeters. And then I weigh about 165 pounds, or force equivalent of 734 newtons, pushing down against your chest. So that force is what it is, 165 pounds or 734 newtons, my weight pushing down against your chest, that force. And so we'll start to set this problem up. Again, I'm going to stand on your chest for the $20, but let's make this magic trick just a little bit more interesting. I'm going to move down a little bit, and so let's move this mannequin down a bit. And when I do this magic trick, I'm going to attempt though to balance on this lag screw on your chest. So now we've changed the problem a little bit. So pressure is equal to force divided by area. The force is what it is, the 165 pounds or the 734 newtons. We haven't changed the amount of force, but what we changed is the amount of area over which that force is distributed, and that's our pressure. Force divided by area is the pressure. And I think that you probably no longer want to do this for the $20 trick. So hopefully that reinforces the idea, the difference between force and pressure. This problem was presented to me where the user's design intent was to find out at what force this block would break. And so down here there's a steel rod placed underneath the block and then a force put onto the block. And let's take a look at how much force though was put on there. So it was actually put on as a pressure rather than force. So if I edit that pressure, I see that it's 4,300 MPa, which comes out in imperial units to about 623.6 psi. So we'll round that off. We'll call that 624,000 psi. And so if I look at the area of this part, I measure this area and I multiply that force times the area. I get a force of about 312 million pounds of force, or about 141.5 metric tons of force on this block. Because those numbers are not reasonable, I think the intention was to actually put this in as a force, newtons, rather than put it in as a pressure. If you multiply that pressure times the number of square millimeters or square inches of that surface, that pressure is rather excessive. But there are several other problems with this. We're doing linear static analysis, or elastic analysis, and so that isn't a measure of fracture. So we shouldn't be trying to do a linear static elastic analysis to determine when something would fracture. And also, when we run a linear elastic analysis, it is only valid on isotropic materials, or that is materials which are the same in all directions, the same material properties in all directions. But a stone or concrete doesn't have uniform isotropic properties in all directions. So that violates two rules of our rules for doing linear elastic analysis. Let's recall some considerations of linear elastic analysis. So with linear static analysis, we're only concerned with the proportional limit from here to here on the stress strain graph. When we go into the plastic deformation, we have to use different types of analysis beyond this proportional limit. When we're doing linear static stress within the elastic range, we are limited within that elastic deformation. So when we take the load off the part, it returns to its original shape. It's assumed that our material is isotropic material. That is, the material properties are the same in every direction. We have a relatively small displacement, a relatively uniform aspect ratio. That is, we don't have a really long, skinny part. The material is not excessively brittle, like perhaps glass. The material is not super elastic, like rubber. And our load is slowly applied. It's not an impact load. In this case study, let's take a look at an issue that a user had where they wanted to suspend a load from the end of a cantilever beam. And what they were concerned with is where this loop would contact just this edge, so that the load would be right along that edge and it would also contact along this edge. Now when we're doing an analysis, we really only need to have the part in that we're trying to analyze. So rather than doing this as an assembly of this part and this beam, we can put the load directly on the beam and we don't need this second part. So let's look at how we might set that up. For this problem, I'm going to make sure that my units are set to millimeters, and then I'll go to the top plane and I will start a new sketch on that top plane, and I'll draw a rectangle to the right of the origin. I'll do a midpoint constraint between this line and the origin, and then I'm going to draw a construction line from the midpoint of this line over to about right there. And let's go ahead and put some dimensions on here. So let's dimension the width of this rectangle as 141, and we'll dimension the height of the rectangle as 30. And then from this edge back to this point, let's dimension that as a distance of 10. And we'll put a circle here at this location, and I intended that to be an object line, so I'll change that back to object line, and I'll dimension that circle diameter, let's say 11.5. Alright, then I'm going to extrude this part, and I'm going to go symmetrical mid-plane 3 millimeters for the total thickness. Alright, if we come over and we check our material, we see that for our material we have steel, and we'll leave that signed as steel. Alright, so we're going to put a load suspended over here, and remember that was on an eye bolt, and so I want to identify the location where that load will be placed. And so I'm going to do a little trick here that's commonly used in FEA analysis. I'm going to start a new sketch on this face, and I'm going to then draw a rectangle about like that, and I'm going to draw a second rectangle over here about like that. I'm then going to put a construction line in between the midpoint of these two, and I'll also put a construction line from here back to the origin. Okay, I'll make these construction lines horizontal, and so I'll select horizontal for this construction line, and looks like that one's already horizontal. And I'm going to intentionally not put any dimensions on these rectangles, or at least not yet. But let's make this line equal length to this line, and I'm trying to decide whether I want to make the distance from here to this edge as a dimension, and then make it the same on this edge. Let's bring this in here closer for now, and so I'm going to leave those unconstrained for now. Then I'm going to do a split face on that, so I'll go to modify, and I'm going to do split face, and I will select this face is what I want to split, and then for the splitting tools I'll select this rectangle, and I'll have to say okay to that one. I need to make that sketch visible again, and I'll do the split over here again. So I'll do split face. Make sure you do split face and not split body. Now I want to split this face, this rectangle, and I'll hide that sketch. So if we have shaded with edges turned on, we can see that we have now a face right here that's planar with this face, and this face is planar with this face. And we'll use that as our location of where we want to put our load. And we can then make this smaller and smaller and smaller, representing that tangent point between the eye bolt and this edge right here, and the tangent point between the eye bolt and this edge right here. So let's do an analysis. We're doing linear static stress, and then I'm going to put a fixed constraint on this end. and then I will do a load over on the other end over here. And so I'm going to put a force load, and let's distribute it across both of these faces, and I'm just going to guesstimate some numbers for now. We may come back and change it. So I'm going to put in 100 pounds force on that, and actually I wanted to do this as metric units on this one. So let's go over and we'll go to the loads, and I will edit this load, and let's do that as 100 newtons. Alright, now I want to see my results in metric units, so let's go to our preferences, and for our simulation, and I want that units to be in SI units. Alright, now if we go back and edit this force, and it converted that, so let's put that in there again. Let's do the 100 newtons, and now it should stay there as newtons. It's still converting it. Oh, here we go. We can change the units. We'll change that units down here. There we go. Okay, then let's go ahead and run an analysis on this. And so we should first mesh it and see how dense our mesh is. And the mesh is fairly coarse. Notice it's a little finer in this area. And I think I'll go ahead and run the analysis at that setting. I'm going to run this analysis locally. And we see our minimum safety factor is below 1, so our load is a little bit too big. We have our deformation adjusted. If we put it on actual, we can see that deformation. And let's reduce that load just a little bit though. So we'll go over to the load, and I'm going to reduce that to, let's say, 75 newtons, and we'll run that simulation again. And so now we see our minimum safety factor is just over 1. And if I go to my displacement, we see we have a displacement of about 0.2 inches, and I wanted that to be in millimeters, so let's change this to units to millimeters, or about 4.5 millimeters of displacement. And if I look at the stress, and I can change that stress to MPAs, and so we see that our highest stress area is back here in this area in here. But also notice, because we have that force at a localized area right in here and here, we also have a high stress area in here. But in the real world, this area probably isn't going to be of concern to us. Now we know that if we put a load right on the edge on that eye hook right here and right here, that eventually this edge is going to get rounded off, and this edge is going to get rounded off. But you have to make a decision, is that important to you or not? But one thing that we can end up with is, in FEA analysis, even if that's not important to us, we can end up with a singularity, or a high stress divided by a tiny area in this area and this area. That will give us a high pressure on our stress reading. So let's make an adjustment to that and see what happens. I'm going to go back to my design environment, and I'll edit that sketch, and I'm going to zoom in here, and I'm going to make that size real small this time. So I will dimension this line, and let's make it say 0.01. So I've made that a real small split area. And maybe we'll drag this, and we could dimension this location. I'm going to drag this area back into here, and I'll do the same thing over onto here. I'll finish that sketch. So now I have a really small area that is split, and actually it's giving me an error here on my split face, so I need to resolve. So I was getting an error on my split with, I went down below 0.02. If I went down to 0.01, then it gave me an error. There should be a logical reason for that. I didn't bother to track it down because I don't think it will be meaningful for what we are trying to demonstrate here. So then I'll go back to simulation, and I need to run my simulation again because we've changed the size of the split face here and here. And so let's run the simulation again. Well, it appears that there is a bug in Fusion 360 in that I'm getting a high safety factor here when low stress, no displacement. Instead of 75 newtons, I did 750 newtons, and it should be showing a singularity or a high stress area here and here. but it's not doing so, and so this appears to be a bug within Fusion 360. So I set up the same problem in Autodesk Inventor, and I put a load, the same 75 newtons of load at these two tiny faces that I changed to 0.01, and it didn't give me an error then when I did it in Inventor. So I had those two tiny little faces, and then when I check my stress, it appears that there from the color that there's no stress, but I see from over here that I have 3700 MPAs of stress. And so if I go to the displacement, I see that I have the same about 4.5 millimeters of displacement. If I go to safety factor, though, I see I have a real low safety factor, and I've introduced singularity here and here by having that load in a really tiny area, applied to a really tiny area. So if I go back to the stress actually is high, but it's in a little tiny area along here and a little tiny area over along here. So we have a high force divided by a low area, and we refer to that as a singularity. We know that that isn't really something that is a problem for our design, so you have to watch out for creation of introduction of singularities like that. For this final case study in lab number 3, let's start a new part file, and I'm going to go ahead and save this, and I'm going to call it block with rib. And I will make sure that my units are metric units. I want to be in millimeters, and I will start a new sketch on the XY plane. I'll draw a rectangle at the origin, and I'm going to dimension the overall width of this rectangle as 300, and I'll then dimension the height of it as 200. I'm going to offset this rectangle towards the inside, so I'll do offset, and I'm going to drag that towards the inside. My offset distance will be 65, and then I'm going to draw a second center point rectangle, and I will draw that from here up to about here, and I'll dimension then this distance from here over to here as 82.5. Alright, so that completes our sketch. Let's now extrude this area right in here, and I'm going to do that as symmetrically, a total of 200 millimeters. And now I'm going to make that sketch visible again, and I'm going to extrude this inside rib. I'll do that as well, 200 millimeters. So I'll select this rectangle, and I want to join that, and for the distance again, I'll go to 200 millimeters. I'll then hide the sketch. Now in the timeline, let's drag the timeline back before we put that rib into the part, and I will go ahead and save this. Our material is steel. We will do an analysis on this part, so I'll go to the simulation. We're going to do a static stress analysis. So in this case study, we want to see what the results would be of adding this support rib to the center of this hole. So first, let's check it without that support rib. So I will go to a simulation, and I'm going to put a fixed constraint on this top face, and then I'm going to do a load on this bottom face of 1 million newtons. And I want to flip that direction, make sure my units are newtons. I'll flip that direction so I have a load of 1 million newtons pointing down. I am then going to run my simulation, and I see that I have a safety factor of 1.96. We'll call that 2. And if I look at the stress, I have a stress of, we'll round that off to 106 MPa. We'll look at the displacement, and we have a displacement of 0.08 millimeters. All right, now let's go back and put the rib back in. So I'll go back to Design tab, and I'm going to put the rib in, and we'll run this again. Now because we've added that rib, our geometry has changed, our analysis is out of date, so we'll have to run it again. So we see that the safety factor has dropped from about 2 down to 1.44. And you might say, well, why did the safety factor drop when we strengthened the part? That was the original design intent, was to strengthen the part. But you have to question, then, what does it mean to strengthen the part? If I go to the stress, I see the stress is now 144 MPa, where in the previous test it was 106 MPa, so that we have increased our stress. And I intended to point out, and I forgot to, that on the previous problem, the high stress area was right in here and over here on these two sides. And now we've moved the high stress area to this center rib. And then if we look at the displacement was 0.08, but now it has reduced to 0.06. So if our definition of strengthening the part is to reduce the displacement, we have done that by adding this rib. The part is not bending as much, but now this is a weak link that has a higher stress in this area than before. The stress was out here and it was out here. Think of it like this. Imagine that I had two weightlifters, heavyweight weightlifters, and they were standing out here on the ends. And then I put a 98-pound weakling in the center to help them. The 98-pound weakling is going to be weaker than the two muscle men that are on either ends. And that stress rises in that center section first, but we did reduce the overall amount of displacement. So we have to analyze these results by more than just looking at the colors. You have to look at the numbers, and you have to analyze what is happening with that part.